So we are at the last of our image manipulation programs. Um, this one is going to treat the image file as not an image. It's going to treat it as an array of numbers, and I'm going to do math on it to show you that you can do math on a picture. Right? And this is how you actually get to all that stuff that the graphic design people and all the rest of them use. For this, we are going to import NumPy. Again, I'm going to do it just in PyPlot. You could do it in the PIL, and you show. Totally up to you. I am going to yank in SciPy for its image ability and image IO, just so I can get the image in and out very, very easily. I define all of my functions at the very top of the file. It's an old habit. It's not a bad habit to be in, quite honestly. So the first one is a vertical gradient, and it gives you notice the three quotation marks, double quotation marks. This is when you call up a function from anywhere else and import it, and you ask it what is it and what does it do. This is where the description is typed. Parameters is literally that. It tells you exactly what parameters this thing takes. What does it get passed and what are they? And then what does it return? And this returns a value. And then you end the three quotation marks. That's like the documentation for your function. If you are writing functions, if you're writing a lot of functions, this is a really good thing to do. Especially if you want someone else to, you're trying to make your own library, and you want somebody else to use your library or be able to use your library later on. This is a way to generate extra user experience, because this is going to make it very, very clear as to what it does and why it does it. I highly encourage this. I also, so a number of columns, I just take the image shape. So whatever the image was that you passed this thing, is going to figure out the number of columns. If reverse is true, then it's going to do that. If it is not true, it is going to do this. By default, it is false. I could just take this out and I could have it pass the parameter. And this will just tell you whether you are going increasing top to bottom or increasing bottom to top when you do this. And then the horizontal gradient does exactly the same thing, only here it's the number of rows, not the number of columns. So I'm just going to yank in that image. It's the same image we've been working with. But this time I'm going to yank it in as type float. It's going to be an array, not an image. So photo is going to turn out to be an array of numbers. Then I am going to put a Gaussian filter on it. To do this, I'm going to take photo with a sigma of 5. Now, if you are familiar with statistics, a sigma is the standard deviation away from the midpoint. So it's going to take the midpoint of this thing and go off basically 5 standard deviations. And then it's going to apply a Gaussian filter to that, and it's going to stuff it into blur. I am then going to plot that figure. I want to show blur with the axis off. And then I want to go out 1 standard deviation, and that's F blur. And then I want to do that one. Sharpen an image. I want to take blur, which was the thing we screwed around with before. And then add 330 times blur minus f blur. It doesn't seem like that's going to make a whole lot of sense. I've just blurred it once, but then f blur only went out one standard deviation. So I'm basically going to try and subtract off the blurring, which could be the original image, if the original image was a little bit blurred, and then blur it a little bit more, just one standard deviation out, and then subtract that, multiply by 30, and then add it back. That should try and take it back to a certain level of sharpness. You're then going to take a sharp, that value, that bunch of values, and then you're going to pull out the max value and divide every single number by that. If you get any negative values, you're going to set them equal to 0. That's what that sharp less than 0 equals 0 means. Any values in the array which are negative, you just set back to 0. Then we're going to just plot that sucker out. And then you want to put noise into an image. Most of the time you want to denoise an image, but if you can figure out how to put noise in, you can always take noise out. Notice that this is a random number generator. So it is generating a set of random numbers which you are then going to multiply and add by a value and then add back to the original photo, and that will give you your noise for this. And then of course, if I add noise, I should tell you how to take noise out of a photo, so this is how to denoise a photo. All of these could have been their own functions. There is nothing wrong with that, writing them all as their own function and just calling all functions and just plotting the thing. I prefer just to do it this way. It was quicker, it was dirtier, and it just got me to give you the answer. Notice that I took a lot of the noise, a lot of these lines, and I chunked them together. You can chunk a lot of this into the argument of the actual plot, and it will again do parentheses. It will do all the math inside, do all the logical comparison inside, and then do the plot at the outside. And then I call horizontal brush, which is the vertical gradient, and the vertical brush, which is the horizontal gradient, for the thing. So let's see what happens when we run that. Again, it's all going to appear in the upper right hand corner under the plots tab. I want to look at the variables first, though, to see how some of these variables are going to be displayed. Again, this takes a fair amount. Notice I'm eating 64% of my memory. That jumped from 58 to 64 rather quickly, because this is very intensive, and as I am doing this, there's a lot of very large arrays here. So this is taking a lot. This is an array of 64 floating 64-bit floating point numbers. So that's huge. That is why my memory has been sucked down. Notice that again they are in alphabetical order, not when they were called. So photo is not. I imported it as a floating type, but they are all 0 to 255. It's an image. There's nothing wrong with it, being an image. And then I go to blur, and notice now it's definitely floating point. I go to F blur, it is floating point. So that's there, and now I go to sharp, and sharp has become floating point, but it's all between 0 and 1. So that is why we had to do sharp divided by sharp max, and anything less than 0 right? Any negative values just be made 0, right? And that's how it came out. Tinted, notice these are scientific notation, right? But they are essentially, even though they're floating point values, they are between 0 and 255. Notice that vertical brush is again going from 0 to 255. Let's take a look at what actually happens here. All right. So that's blur, and that's basically what you got from the PIL from before, the Python image library. When you called the blur function, it looks almost exactly the same. I worked very hard at figuring out what the sigma had to be for this thing so that we got an image which looked basically like the blur from the PIL. If you do it a little bit less, if instead of going 5 you go 3, you will get less blur. If you go 7, you will get way more blur. Right, so just play with the number. I mean, rerun the program. It doesn't matter, right, what photo you feed it. But just feed it stuff and see what it does. Right, this is the sharpen, right, and you notice that it is slightly less blurry, right, and I left on the axes, right, just so you could tell the two blurred apart. If you make them a little bit bigger, right, you'll notice that this one is a little sharper. It's not as bad. Right. This is the original, right? And that's how to put noise into an object. Right, and this is taking noise out of an object. Right, tinted. Right, which changes the sharpness a little bit. And now this is my vertical gradient and my horizontal gradient. Notice I have it set so that it goes from left to right and bottom to top. If I changed that parameter that I passed it, which was the logical parameter, if I changed that to a true, then this would tint from right to left. So the dark would be on this side, the light would be on that side. And if I change this to true, this would go from light to dark. The dark would be at the top. That's all there is to it. Now, there's a little bonus. What I've got, let me get rid of this. Is and dump the variables. So we can go back. This is one of the things that I've been working with and started using. This is when it says FITS manipulation. FITS is an astrophotography file format. And so what I do is I pull in PyPlot just again, but this time I pull in AstroPy. AstroPy is a library of astronomy-based image manipulation tools for everything. And so I just want to import that as FITS. And so I'm going to use that FITS to open up a FITS file. I am then going to import, print the information from that file. This is really, really, really important. Every astronomy FITS file has a header to it that tells you the telescope and the location and the filters used and all kinds of other stuff. Then I want to strip off the header. I want to print the header. But then I'm going to strip off the header, and then I'm going to save just the data, which is just the image, down here. And then you have to close the astronomy file. You have to close the the FITS file. Before you start manipulating the new stuff, just the image, please make certain you close the FITS file. Otherwise, bad things will happen to good people. This is one of the few times I have crashed both my Linux box and my Mac, is when I've written programs like this or been playing with functions that I've started to write for image manipulation for astronomy, and I have failed to close the FITS file before doing stuff. That's when I have crashed the box. So please make certain that you do this. I cannot stress that enough if you're going to be messing around with FITS files. So let's run this and see what we get here. And again, this takes a fair bit of time. Notice that it sucked down a fair bit of memory. When I go with the plots, this is imagery of the moon. It's not that, it's an image of the moon. Notice that it's pulling down. It opens that file, which is moon FITS. That's your ASTR file. Type is input output FITS file. And it's really struggling to give you information here. This is your header object for the file, and now you have stripped it out, and you've got a 0 to 255, supposedly. Notice it's not. You got a 269, you got a 286, you got a 287. It should be grayscale. It should be 0 to 255. It's not. It actually goes up to 512. So you got to play around with that a little bit, just so you know. But the first thing that we are going to show, of course, is when I print that. I'm sorry, where am I? I want to output the figure. That's the original. Notice I didn't strip off the axes. This thing is ugly. It's got way too much dark on that side. So we would like to crop this, and we are going to get to crop that in a minute. But the other thing that plot will do for you is this command right here, color bar. And notice it gives you the grayscale and the gradients right here. That's really helpful. For FITS files, this is extremely helpful. The axes on the actual graph, no, but the gradient scale turns out to be really, really helpful. And then I cropped it. You notice that it's figure size 15 by 15, and then I image cropped that thing. Excuse me. 25, 450, and 401. You can locate. That's the nice part about this. You can locate pretty much where the top of the image is, where the bottom of the image is, where the left side and the right side are. That gives you your X extent. That gives you your Y extent. And I can put them right in here, in that image crop. And then I can just plot that thing, and I can do it as a gray map. Notice that the header file gives you all kinds of information. That was that print, and I said print header. Holy cow. It gives you the file name, version, type, dimensions of the image. That's the camera size. They always go by the pixels, X and Y. 16-bit integer, for your file format. It conforms to FITS standards. BitPix at 16 bits per pixel. Right, this gives you 650. Right, is the width of the table, 500 rows in the table, file name. It tells you the equinox, where it was taken, Greenwich Mean Time, the time it was taken, the date it was taken, which is 2010. Oh my gosh, right? There's tremendous amounts of information. Right. It even tells you that the telescope it was taken from has a name. It's Cecilia. Right. The temperature of the camera. Right. The ambient temperature. It's all in Kelvin. Right. Outside. Right. The humidity during the observation. Right, this was taken at the Smithsonian Center for Astrophysics. Is where I got this particular thing. It gives you a reference and where the telescope is located. It's in Arizona, United States. Right. And in this particular case, it actually tells you, warning, the file may have been truncated. The actual file length is smaller than the expected file size. I did mess with this a little bit before using it for this demo. All right, so in any event, all right, there we go. All right, you got bunches of information, right, and you've got ways to be able to manipulate and play with files. We will get to loading more files and doing statistics, and graphing those statistics a little bit later on in a different one. We will not use pandas, but if you can understand the basics that I am going to give you, you'll be able to understand pandas, and you can use that at any point.